I'll recognize Mr. Weber for 5 minutes.
Thank you, Madam Chair. Well, first of all, let me do it this way. Dr. Williams, how long have you been involved in the quantum field?
So I formally, NIST has had a program since the year 2000, and I've been engaged in there. I was at the first workshop that I think was solely focused on QIS back in 1994 that was held at NIST, shortly after Peter Shor came up with his algorithm.
Okay, Dr. Kurose.
Well, I have an undergraduate degree in physics and learned quantum mechanics as an undergraduate, but my involvement with QIS research began when I came to the National Science Foundation 3 years ago.
Okay, so that's 2014. Dr. Binkley.
I did my PhD work in quantum chemistry and got my PhD in 1976, and I've been involved in quantum theory and quantum-related work ever since.
Well, good gracious. Okay. You should be a quantum leap ahead of everybody else.
Sir, I'm afraid it's a terribly difficult subject.
I understand. Dr. Kurose, your written testimony touches on the differences between classical computing, like the exascale computing systems we've heard so much about in this committee, and quantum computing. Explain the difference for us as briefly as you can.
Okay, well, in traditional supercomputers, for example, information is stored in bits, ones and zeros, and we operate on those bits. So we perform operations, additions, multiplications, and all kinds of transformations. That's the way computing technology has been done since its invention 70 years ago. Qubits, as my colleagues with PhDs in physics can tell you better than I can, are very different beasts. They don't exist in the 1-0 state. They exist in a superposition of states. And from a computing standpoint, that allows one to, rather than compute deterministically over ones and zeros, to deal with the probability distributions of how the states of the qubits are and the entanglement, the interrelationship between these qubits. It's a fundamentally different way of thinking about computation and moving from ones and zeros to these qubits.
Okay, to an identifiable state, either 1 or 0, to now to a single particle that has the ability to do both.
Right, and I would say in the end, you need an answer that has ones and zeros, and so there is going to be a very important coupling between the digital systems that control and program these quantum computers and the quantum technology that's lying at the base underneath them.
So, very quickly then, what you're saying is that these two systems will interact, because you just said in the end, you need the ones and the zeros, the binary code.
That's right. So the traditional computing will play a very important role in terms of the programming and the control of the quantum computing. And I'd mentioned earlier, the fact that you can now program quantum computers using the digital programming to sort of wrap around the quantum.
So we're going to hear about that in the next panel.
I think you'll hear about that in the next panel.
Dr. Binkley, for you, we've spent a lot of time on this committee discussing high-performance computing, particularly DOE's goal to create an exascale computing system by 2021. How does the push to study quantum information systems fit in with that goal?
At the Department of Energy, we see quantum computing as something that follows the efforts that we're doing in exascale computing. There are classes of physical problems that are characterized by the Schrödinger equation, which is the basis of all quantum mechanics. And for example, most of materials and chemical sciences fall into that category. Today, we do calculations of an approximate nature on digital computers for the purpose of furthering our knowledge in those areas. Quantum computers will enable us to do much, much better calculations, exact calculations, as it were, when they finally become available. However, there will still remain applications in high-performance computing that are not quantum in nature.
Back to the ones and zeros you talked about.
Back to the ones and zeros. And those calculations, for example, structural calculations of materials, looking at doing engineering types of calculations, looking at nuclear fission reactors, looking at heat flow, and things like that will still remain inherently digital. And so there will be a continuing need for simulations of that class.
So you foresee a parallel path, quite frankly?
Yes, sir. We see the two different technologies as being very complementary in the future.
Madam Chair, can I indulge for about another 2 or 3 hours? This stuff is fascinating. I yield back.